Good morning. So we've got 4 of my videos left, Thursday, Friday this week, Thursday, Friday next week. And rather than get into year 2 stats or mechanics, Mr. G and I have decided that I'm going to do a little bit of proof, mainly just recapping the stuff you did earlier in the year. Proof features in both year 1 and year 2, and it'll set us up nicely, or set you up nicely for what you need to do in year 2. So I'm going to start with a quick recap of what I call GCSE proof. So this is what you would have done at GCSE. So just a few sort of reminders. I'm looking at the left-hand side here to start with. If proof questions talk about an even number, then you describe that as 2 times something. So I've used 2a, and it could be 2a, 2b, whatever, where n is an integer. If we talk about odd numbers, then we can describe it as 2n plus 1 or 2n minus 1. It's always one bigger or one smaller than an even number, where again n can be any letter and n is an integer, a whole number. So if a question talks about 2 different even numbers, then we've got to use 2 different letters. 2a, 2b, 2m, 2n, whatever you want. But if a question talks about 2 consecutive even numbers, so they're related, then if we call the first one 2f, then the next one will just be 2 bigger than that. Or it could be 2f minus 2. Again, I can use whatever letter I want. And then if we've got to prove that something is a multiple of, say, 3, all we need to do is to write it as 3 times something. And if we want to prove something is a multiple of 5, then all we need to do is write it as 5 times something. So here are 2 separate examples of that sort of question. Please note that this question, it should be 3 consecutive even integers, even numbers, whereas this one doesn't mention consecutive at all. So I'm going to pause the video, have a go at those 2, and then I'll come back in a second with my solutions. Okay, so 3 consecutive even integers. So here's my first one. The next one will be 2 bigger than that. And the next one will be 2 bigger than that. You could have had 2n, 2n minus 2, and 2n plus 2. Same difference. And the sum of means we add those together. So when I add those together, I get 6n plus 6. I've got to show that this is a multiple of 6. All that means is writing it as 6 times something, and bingo. So I would then say, which is a multiple of 6, and then that little phrase, which I really like, finishes off a question nicely, as required. That's what you wanted, as required. Okay, 2 odd numbers, not consecutive. So I'm going to call one 2a plus 1, and the other 2b plus 1. Product means multiply, so I've got to multiply those 2 together, and whenever I multiply out brackets, I grid it out. So there we go. So I've got here 2 times 2 is 4, a times b is 4ab. I've got a 2b there, and I've got a 2a there, and 1 times 1 is 1. So if I add all that up, I get 4ab plus 2a plus 2b plus 1. Now, I know how to show something's a multiple of 6. There. How do I show something's odd? Well, you show it's odd by showing it's 1 bigger than something which is even. Even is a multiple of 2, so I'm going to write that as 2 lots of 2ab plus a plus b. So this bit here is an even number, because I can write it as 2 times something, plus 1. 1 bigger than an even number is odd, which is odd as required. Now if you go to the GCSE section of Maths Genie, and look under grade 9, they've got a really good set of questions on proof. You may well have done them when you were revising for GCSE, but if that was a bit of a head scratcher, I would certainly recommend that you paused at this point and went off and did a bit of that. So at A level, I would suggest that there's another sort of algebra that we need to introduce, along with that for an even number and an odd number and consecutive even numbers, etc., etc. And that's the concept of a rational number. Now, we're familiar with irrational numbers. It's numbers like pi and the square root of 2. But a rational number is the opposite. So a rational number, its formal definition is any number that can be expressed as a fraction. So if a and b are integers, whole numbers, then a rational number is always obtained by a over b. And so questions that talk about rational numbers, we would define a rational number in our proof like this. So let's talk about the first of the 3 sorts of proof that we need to be able to do in year 1, and that's proof by deduction. Proof by deduction is where you use known facts, and this is algebraic facts, to show that something else is true. What do I mean by a known fact? Well, for example, if n is an integer, then I know that if you square it, you're always going to get something bigger or equal to 0. So even if n is negative, I know when you square it, you get a number that is bigger than or equal to 0. And the fact we've just talked about is also what could be described as a known fact. If a and b are integers, a over b has to be rational. Just a reminder, integers can be positive or negative, okay? They're just whole numbers. Here's the key thing though. When you answer a proof by deduction question, you really ought to start with the known facts and end with the statement you are trying to prove. Let me demonstrate what I mean by that with an example. So here's an example. Prove that for all positive values of x and y, this sum here will be greater than or equal to 2. So I'm going to start with the thing I'm trying to prove. I know that's the thing I've told you not to do, but this is just as an example. So if I want to add those 2 fractions, I need a common denominator. So I need to multiply that one by x and that one by y. 8 fractions, so I'm going to multiply both sides by yx. Does anyone mind if I write that as xy? Okay. I'm then going to subtract that from both sides. And then this is something that only comes by experience. You need to realise that this is something that can be factorised, and it factorises in quite a nice, easy way. It factorises like this. Let's just check that. Minus y times minus y is y squared. So I end up, yeah, so that does factorise to that. Now, I know, do you remember what I said? Anything squared is always going to be greater than or equal to 0. So I know that whatever is in that bracket, positive or negative, when you square it, that's going to be true. So this is a known fact, and I've got to that known fact starting with the thing I'm trying to prove. So I've sort of done the work I need to do to solve this problem, but I've done it backwards. And I think you have to do it backwards in order to work out how to do it. But I think then in your solution, you need to rewrite it the other way around. So in my actual solution, I would have this as my rough working, would never cross it out. I would perhaps say, rough working. And then I would say, right, here's my solution. I know that is true. And I don't think that needs any explanation. I think the people marking A-level papers are A-level teachers or retired A-level teachers, so they know that's true. And then I'm just going to run this in reverse. So if you expand that, you get this. You then add that to both sides. You then, what do we do here? Oh, we divide by xy. Sorry, and that should be x squared, shouldn't it? Sorry. So we've got x squared, y squared, divided by xy greater than 2. Actually, I should have, when I multiplied by xy here, I should have said the only thing you need to remember with inequalities is if ever you multiply or divide by a negative number, you swap the inequality sign. But because we are told that x and y are both positive, then that's positive. So I didn't have to worry about it here. And similarly, I don't need to worry about it here when I'm doing the reverse, when I'm dividing by xy. So all I'm doing is running this in reverse. So that is the same as required. So you don't need lots and lots of explanatory writing. You just need to show your steps clearly, which were these steps in reverse. Now, what if you just did it that way in an exam? Well, actually, looking at mark schemes, and we're only a few years into this, it looks like you're okay. It looks like you're okay. It looks like if you do it this way and just leave it like that, perhaps putting, which is always positive there, you're okay. This is the proper way of doing it, and I'm not doing my job if I don't teach you the proper way of doing something. Okay, here's one for you to try, and again, I'll pause and we'll have a go in a moment. Okay, two rational numbers, so I'm going to call one a over b and one c over d, and this is my rough working over here. So if I multiply those together, I get AC and BD. So if A and C are integers, and AC is an integer, you multiply two whole numbers together, the answer is always a whole number. And ditto, if B and D are integers, BD is an integer. So that's my rough working, and all I'm going to do now is just sort of do my proper solution in reverse. So I'm going to say, right, consider integers A, B, C, and D. AC over BD is rational. Has to be rational because that's two whole numbers multiplied together, that's two whole numbers multiplied together. Therefore, have you come across that before? 3 dots. Therefore, AB times CD is rational as required. Easy peasy. Started with a known fact, ended up with the thing I was trying to prove. Second example, again, I would do some rough workings and then I would do a solution. Pause and I'll come back in a minute. Okay, so here's my rough working. So I've got x plus 6 squared is greater than that. If I grid that out, just for once I won't do it, but I know this is what I would get. If I multiply that out, take away 2x from both sides, take away 11 from both sides. then I spot that this can be factorised. And I'm there, aren't I? Because this is something squared, and I know anything squared is always going to be greater than or equal to 0. So here's my solution. I'm going to start here. Doesn't really need any explanation. I know that that's going to be true. So you then just run that in reverse. So expanding the brackets gives me this. You then add 2x to both sides and add 11 to both sides. And then you show that that factorises to give you this. So proof by deduction. Start with something you know is true and end up with the thing you are trying to prove, having done a little bit of rough working first. One more example to go. Here's your third one. Sorry, this says 1 over a plus 1 over a. Actually, the previous question as well referred to real numbers. So real numbers are any number, not just whole numbers. Okay, so positive real numbers, so that's anything from 0 up to infinity. So see if you can have a go at this one. Again, rough workings, proper solution, see where you get. Okay, so in my rough workings, I started with the thing I'm trying to prove. I multiplied everything by a, and as a was positive, I didn't have to change the inequality sign, and I think it's worth just making a note of that. Took away 2a from both sides. So these nearly always involve getting a 0 on the right-hand side, don't they, these inequality ones? And then realising that this can be factorised. So something squared I know is always greater than or equal to 0. So in my solution, I just run that in reverse. I start with the thing that I know is true, start with known facts. I expand it, I add 2a to both sides. I then divide everything by a, which is okay, as a is positive. I don't need to flip the sign, and that gives me what is required. Okay, 2 practice ones for you. I've attached a worked solution to these rather than going through them in the video. With this one, I would start by squaring both sides, remembering that squared, you've got to grid it out, and hopefully you're okay with that one. Find the mean, add them together and divide by 2. Yeah, hope all is well. So tomorrow we're going to stick with proof by deduction and look at a couple of other sorts of questions.